Hello everyone and welcome back. Today we're going to talk about Descartes' rule of signs, and in particular why we care and kind of what this guy did. So the problem. So any nth degree polynomial can have at most n zeros. So some have fewer. So that's fundamental theorem of algebra, right? We know if we have something like x to the 6 plus 5x squared plus, I don't know, like 3x minus 2, we know that it at most is going to have 6 zeros, but it could also have fewer than that. And so how can we tell exactly how many positive or negative real zeros a polynomial has? Well, enter this guy. This is Rene Descartes. He solved that problem for us. So now we have kind of more clarification on, okay, we know we have at most 6 zeros here, but what can you tell us about how many positive I have, how many negative I potentially have? And in the next video, we'll see this will help us figure out, okay, well, what are the zeros? So all that being said, thanks, Rene. So what this guy figured out is he figured out that if p of x is any polynomial, then the number of sign variations, so anytime you go from plus to minus or negative to positive, that will tell you how many positive zeros you can possibly have. So, and it's the number of sign variations or multiples of 2 less than the number of, let me move this. The number of negative zeros is the number of sign variations of the negative version of the polynomial, so p of negative x, or multiples of 2 less. And it's less confusing than it sounds because there's no real way to say multiples of 2 less, but in practice it looks much easier. Okay, so let's see an example. So example 1, since Rene is French, we are going to do French. And let me keep moving my pen around. There we go. So how many positive and negative zeros are in this particular polynomial? Well, the first thing we're going to do is we're going to count the sign flips. Okay, so there's a positive to negative, there's 1. Negative to positive, there's 2. Positive to positive, nope. Oh, there's a change, and there's a change. So that's 1, 2, 3, 4. So then there could be 4 or 2. This is what I mean by multiples of 2 less. Now we're just going to count down by 2. So there could be 4 or 2 or 0 positive zeros. So that's how many positive there could be. Now let's see how many negative there could be. Well, we need to figure out what f of negative x is. Okay, well, f of negative x is just going to be negative x to the 5th minus negative x to the 4th plus 3 times negative x to the 3rd plus 9. And I was criticized how I make my 9s. There's a nice 9. Negative x squared minus negative x plus 5. Whew. Okay, all that to just basically say, okay, what are our signs? A negative to an odd power is still going to be negative. A negative to an even power becomes positive, but then, so that turns positive, but then we have the subtraction out in front. Let's see, negative to an odd power is negative, so this will change. Negative to an even power, that's positive. And a negative, that changes. And positive 5. Okay, so how many sign flips here do we have? Nope, same. Oh, there's a change. Same. So 1. So therefore, we could have 1, or if I go down by 2, it'd be negative 1, so that's not possible. So I'm going to have 1 negative 0. Okay, so I'm going to have 1 negative 0, and then I possibly have 4, 2, or 0 positive zeros, and the rest of them are going to be complex. Okay, so we can have at most 5. Out of those 5, either 4, 2, or 0 of them are positive, 1 of them is negative, and the remainders will be complex zeros. Okay, let's see another example. We will call this example 2, which is French for 2. So how many positive and negative zeros here? Well, again, according to Descartes, this is the positive version. So nope, not a change, not a change, not a change. Oh, here's a change. Here's a change. Nope, nope. Okay. So there's 2 sign changes. So there could be 2 or 0. So we just keep subtracting by 2. So there could be 2 or 0 positive zeros. Positive zeros. Okay. Now let's do the negative version. This is going to be a headache. Negative 4 times negative x to the 7th plus 3 times negative x to the 6th plus negative x to the 5th plus 2 times negative x to the 4th minus negative x to the 3rd plus 9 times negative x squared, that's a negative, plus negative x plus 1. Can't even say that all in one breath. Okay. A negative to an odd power is going to stay negative. And I don't know why I have that out here. Disregard that. That doesn't belong there. So a negative to an odd power is going to be a negative. So that'll be negative 4. I think I was just getting ahead of myself. A negative to an even power becomes positive. So positive is positive. 3x to the 6. Negative to an odd power is negative. So negative positive is negative. Negative to an even power is positive, so positive, positive, so positive, 2x to the 4th. A negative to an odd is negative, so and then we have negative, negative, so that'll be positive. Negative to an even power is positive, 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 so stays positive. Negative, positive, that'll be negative, plus 1. Okay, number of sign changes here. There's 1, there's 1, there's 1, nope, nope. There's 1, and there's 1. So that's 1, 2, 3, 4, 5. So then we will have 5 or 3 or 1 negative 0. Negative 0. Okay, so amount of positive zeros could be 2 or 0. Amount of negative zeros is 5, 3, or 1. Again, we always go down by 2 until we kind of run out of space. Alright, so that in a nutshell is Descartes' theorem. Thanks, Rene Descartes. Now we can have an upper bound on how many positive and negative zeros we have. This will help us in our future video when we're trying to find all the real zeros of polynomials by hand.